Okay, so let's continue where we left off. We've taken a look at these filters. So we've seen an identity filter, we've seen an edge filter, we've seen how to sharpen the edges. We've also seen how to have a filter which has the original image and plus a sharpened edge, right? And we've also seen how to blur the image. Okay. Now let's take a look at how to apply it to a two-dimensional case. Okay, so here's an example which I've taken from Wikipedia. So let's see if we can apply the same concept to a two-dimensional image. So if this is the input image over here, and we want the identity image which is supposed to replicate it, what should the two-dimensional filter be? Same as image, should it be all ones? One in the middle and all the rest should be zeros. So does anybody agree or disagree with that? So what you're saying is that it should be maybe an identity matrix, something like this? That's a good question. Why is it? Which one should it be? It's not clear. Okay, you have, if you're doing matrix multiplication, you've got the concept of an identity matrix as well. Okay. So so should it be the identity matrix or should it be this matrix? So this one will start detecting. So why do you think it's not an identity? Well, let me tell you, the correct answer is this, but the question is, why is it this and not this? Okay, so we've seen that this particular filter will actually be detecting a left diagonal, right? But again, it comes. The question is, we've used in matrix multiplication. We've seen that the identity matrix is often used when you want to duplicate the original matrix, right? So why is the identity matrix not working here? Why is it detecting a left diagonal? Exactly. So we're not doing matrix multiplication, right? So we're applying a filter, we're doing convolution. Convolution is very different from matrix multiplication. So in a convolution, what we do is we take the entire filter, we just place it on a particular edge, we do a point-to-point multiplication, and either we keep the entire sum or we divide the entire sum by normalize it by taking dividing it by the number of pixels, right? Normally you normalize it, sometimes you don't, okay? But you can see why the identity matrix, this is wrong and this is correct, okay? So this is the correct answer. And this will produce you the identity matrix. Now, so you can see that this was similar to what we had seen in 1D. Now, the only difference is that it has been extended to 2D, okay? So it's identical in this way as well as vertical, okay? Now, what about the edge detection? Can you think of an edge detector? Simply edge detector. Now, can you see this image? You can only see the edges. I don't know if that's visible to you, but the images are slightly visible, okay? And here you can see that this is a sharpened version of that image, okay? Is that visible to you? Okay. And this is the one which had the original image plus the sharpened images. And this is the one which had the blurred images. Now your challenge is to figure out from one-dimensional to now you convert it to two-dimensional. So what should be the edge filter? -1, 2, -1, okay. So यहाँ पे क्या आना चाहिए? 0, -1, 0, 0, -1, 0. Okay, so that's good. That's exactly what it's supposed to be. I won't show the zeros normally. So this is your edge detector. Okay. Now, if you want to sharpen it, this is a little bit sharper. If that's visible to you, what would you do it? Actually, this is a different example. So this is not, this is the sharpened image. Okay. So these two are almost identical, but this is to show you that you can have a different type of sharpening, as a different type of edge detection as well. So what is unique about this? Why do you think it's it's an edge detector only? What's the property of this entire filter? Is this right or not, by the way? हमने कोई गलती तो नहीं कर दी इस filter में? What did we say was the property of the filter? That it has to
sample value 4 आना चाहिए.
Come to 0. So what did we do a mistake over here? Sorry, it's not balancing, right? The total sum is coming out to be -2. Is that right? So should the filter only be, should the filter be normalized to 0, right? How can we do that? Sorry? Divided by the total. No, वो फिर भी divide -2 by 100, it'll still be a non-zero, right?
We can have a 4.
So आप क्या कर सकते हैं यहाँ पर? Negative or positive? Okay, so you could make it 0.5, 0.5, 0.5, and 0.5. So now you have a zero edge detector, right? So it's detecting now, but since it's a little bit unusual, because आपने देखा था कि यहाँ पर this was detecting a filter like this. This was your typical one. लेकिन यहाँ पर जो है is doing something different, right? So along the diagonal, so you could do this, but this is not what is the, I don't know what this will produce, but let's go back to the basics. We have a problem over here that you have -1 and this not balancing out. What's the simplest way to balance it? 2 के बदले आप 4 कर दें, exactly. So this would make it a filter, a proper edge detecting filter. जी. वो गलत नहीं था. It's just that I don't know what it will produce. Okay, but this we know what it will produce, because we can see that it seems to have a filter which has similar properties, but the only difference is that the 2 over here is replaced by a 4. Why do you think it's replaced by a 4? If you think about it, what we've done is हमारे पास इस तरफ जो 2 था वो हमने 2 किया, और इस तरफ जो 2 था वो भी हमने 2 डाल दिया. Okay, so diagonal अभी भी balance नहीं हुआ. So you can play around with different filters. You can think of different filters. In fact, that was the purpose of this filter. This filter, as long as the overall sum is coming out to be 0, is going to be an edge detector. Now, how do you design that? For example, you could have, here's another example. Again, on the same site, this is a 1, 1, and a -1, -1. Okay, this produces this image. Can you see that this image, if you look closely, is not very different from this? Of course, a different hair, lekin not a whole lot. Okay, so even this is an edge detector, but because the sum is coming out to be a 0, the यहाँ पर भी sum is coming out to be a 0. Okay, the idea here is that this is a 4. Okay, so you could design different types of filters as long as there is some kind of somewhere you can see the overall values are coming out to be 0. Okay. Acha, that's a good point. That's a very good point that you picked up. कि ये जो है, it is making this particular row 0 and this particular row 0. So you can try to figure out more details into it, but that's a more advanced topic. Let's take a look at this. How would you make an image sharper? So you take this particular edge detector, you want to make it sharper. What can you simply do? Multiply it by 2, so you could make it 8 and minus 2, minus 2, minus 2, minus 2. Okay, and that is in fact this particular image. No, actually it's not like this. This actual image is based on the following values. -1, -1, -1, -1, and a -1. So you can see the totals is coming out to be 3, 4, 5, 6, 7, 8, and -8 plus 8. So the total is coming out to be 0. Okay. Why was it? Sorry. So why didn't we do the earlier one, right? But I'm just telling you that both of these can be used. You can try out different types of filters, and they'll have slightly different impacts. But our focus right now is not really to spend too much time on looking at what the impact is of different filters, but just to give you an idea, as long as the overall thing is coming out to be a 0, it's going to an edge detector, and somehow you can see the center over here is large and the peripherals are negative. Okay, so there has to be that kind of a balance. So this is a sharpened image. Okay. Now, what do you think this filter should be designed to be like? What should be the average value over here? Should the average value come out to, should be a 0, like a 0 over here? All of these were average zeros, right? And that's why you could see that they were only getting the edges, right? अब आपके पास original image भी है, and the image has been slightly sharpened. Compare this with this. Can you see that? Can you see that this particular image has got sharpened? The edges are a little bit more sharp, okay? And the background over here, now it's more, previously this was, fairly blurred, but now you can actually see the differences, okay? So if there was some image over there, some bird over here, that will be more visible. So what do you think this particular filter should look like? सबसे पहले sum इसका क्या होना चाहिए? Sum 1 होना चाहिए, right? It has to be similar to the identity matrix. So let's design a filter which sums up to 1, but is also an edge detector. So can you tell me some simple solution? Sorry? So say that again. First and the second filter. तो हमने ये filter और इस filter को add कर दिया. That's a simple solution, right? So what do we get? We get a -1, 5, -1, -1, and a -1. Okay, and in fact, this is exactly the image. This is exactly the filter that has been used over here. Okay, but we could make changes to it. For example, we could combine this with this as well. Okay, we could combine any one of them with the identity filter. Okay, what about this one? Ji. So let's say this is filter number F1, this is F2, this is 3, 4, 5, and 6. 6 filters, right? तो आप फिर से कहिए आप कौन से 2 filters को ऐड कर रहे हैं? 1 और 2 को हमने ऐड कर दिया, यहाँ पर 1 है और 2 को हमने ऐड कर दिया, and we got this, right? This is 1 plus 2. Okay. So if, for example, you have an even sharper image, what you could do is you could double all of these values. उसमें होगा ये कि ये वाला image बहुत sharp हो जाएगा. अगर आप, for example, यहाँ पर 1 और 2 के बदले you do 1 and 3, 1 and 4. So what do you think you'll get over here? You'll get this. You'll still have the original image, but the edges will become too sharp. They'll start to dominate. So if it becomes too dominant, then actually the image will become, it won't look nice because आपने edges को इतना sharpen कर दिया कि अब edge रह गया, original image खत्म हो रही है. Okay. So obviously you've got to have a balance. You can't have too much edge sharpening when you're doing these filters, you don't want to over sharpen this. Okay. Blurring के लिए, can you give me an example of a blurred filter? So सारे ones आप कर दें and multiplied by 1/9. Very good. So multiplied by 1/9. So the average comes out to be the average comes out to be a 1, right? So that means that the original image is being retained. It's sort of similar to the identity matrix, but instead of being a 1 right in the center only, it is being spread around. Okay. So as you've seen in the earlier image, कि जब आपके पास spread out हो जाता है, 1/3 को आपने यहाँ 1 को आपने split कर दिया into 1/3, 1/3, 1/3, so the edges get spread. Okay, so the edges are getting blurred. Okay, so this is exactly what you get. This is exactly what filter was used over here, and you get the same image, but the edges are now blurred. Number 2 and number 3. You're late, and so I'm repeating again, but very quickly. देखिए इसमें फर्क ये था कि this was an edge filter. Okay, this was also another edge filter. Okay, it's not different, but it's just another edge filter. 2 or 3 or 4 में फर्क ये है कि 4 is a more sharpened version. Okay, and 2 and 3 there's no difference. Okay, it's just 2 different versions of an edge filter. Okay. Okay, so so now you have some idea of what filters do. Okay, in an image. Okay. Now I'm going to take a look at another example. So to give you several examples, I'm going to look at this particular example. Again, you can take a look at it. And when I normally put a time over here, this is the time where interesting thing starts. Okay. So here's a filter. Here's an example. And what they've done is they've taken a filter of an image which looks something like this. Okay. Maybe it's a 7 and it's filtered upside down. All right. And now they've applied different types of filters. They've applied 4 filters. And now my question to you is, what do you think these filters are doing? What do you think this filter is doing versus this filter versus this versus this? Okay, so first of all, is this an edge detector? Well, the sum is total is 0. Sum total is 0, sum total is 0. Okay, so clearly these are all edge detectors. Okay, now if this is an edge detector, what do you think is the difference between let's say filter 1 and filter 2? Okay, filter 1 and filter 2, क्या difference लग रहा है? Horizontal and vertical. So this is probably, which one do you think is detecting a vertical line and which one is detecting a horizontal line? Filter 2 is probably looking at vertical lines and filter 1 is looking at horizontal lines. Remember when we were saying कि हमें O detect करने तो we need to have an okay. Now, what do you think is the difference between filter 1 and filter 3? Because notice now, both of them seem to be, what do you think, is filter 3 also doing something horizontal or vertical? So this is also horizontal. This is also horizontal. Okay. And these two seem to be vertical. This is vertical, this is also vertical. But now what do you think is the difference? This one, filter 1 and filter 3. Upper and lower edges, right? So if you've got an image like this, which has got a fair amount of width, so one of them will probably be detecting as you go from, as you're going from top bottom, it should be able to differentiate between going from black to white versus going from white to black. Okay, so and what do you think these two filters are doing, the vertical filters over here? Again, the same thing now. So in a sense, for this particular image, filter 1 and filter 3 should be able to differentiate between the top edge and the bottom edge of this particular guy. And filter 2 and filter 3 should be able to differentiate between this particular edge and this particular edge. Okay, so now let's take a look at the results. Okay. So these can also be thought of as images like this. So you can see -1 can be thought of as a negative black. Okay, a 1 can be thought of as a positive white. So in other words, white is completely high positive, high negative is a black, and a center is a gray. Okay, so so this is how these filters are being represented as shades. Okay, now let's take a look at what we get when we apply it. So now the white over here is representing a positive result. Okay, the black is indicating no result. Okay, and the gray implies it's a 0. Okay, so the gray is a no, sorry, forget about the gray for a minute. Okay, so now what you can see is as you're applying this particular filter, overall it is only detecting edges. Okay, but it's differentiating between these two edges. Similarly, this guy over here is different, has a different result for these two images. Okay, so it's doing the exact opposite. Similarly, this filter over here has a particular result, and this is sort of a symmetric, an opposite. It has a symmetrically opposite result. Okay, so you can see that different types of filters, once we eventually identify them through maybe backpropagation or what have you, they may be able to identify not just vertical edges, but how the images change, how the shades go from, from white to black or black to white and so on. Okay, so just to give you an idea. So now this particular example goes on to show how a deep neural network can now start to identify different images. So now here what we're seeing is the layer 2. Okay, so this is a deep neural network. And in the deep neural network, if you remember, you have the input layer. Okay, and if you're going from left to right, then you have layer 2, then you've got a layer 3, and then finally you've got the output. Okay, so you can think of this as layer 1, layer 2, layer 3, and the output. So we're going to compare layer 2 with layer 3 filters. And these are all activation maps. Okay, so these are activation maps at layer 2. Okay, and there are a whole bunch of these filters. So you can see, you can imagine that this is one set of filter, this is another set of filter, and it's being applied to different images. Okay, so you can see when this particular set is put in as the input, the layer 2 activation maps start to have a resemblance of the inputs. So it's picking out some of the features of this particular input. Okay. If it's applied over here to this particular sets of inputs, then the layer 2 is picking out some of the features of this particular images. In other words, there are lots of sharp edges over here. It's picking out a lot of the sharp edges. Okay, if they are round, a lot of these round edges, then the activation maps are round. Okay, at layer 2. Let's take what do you expect at layer 3? Yes, so this is now at layer 4. Okay, and it's giving you a slightly different results for more complex inputs. Okay, so here is maybe I need to zoom in over here. Control P, I think. Does that allow us to zoom in? Anyway, I can't figure out what is the name. But as you can see over here, that these are birds, images of birds, right? And you can see that in this particular image, the layer 4 has started to pick out a complete images of the birds, right? So you can actually see कि इसका पूरा image नजर आ रहा है. Here you can see that you can see the legs over here, you can see the actual birds. So some of these are picking up different parts of the image. Okay. Here this is being fed in dogs, and you can see that at layer 4 it's picking up quite almost the entire faces are coming out in the activation maps. Okay, so as you're going deeper into the deep neural network, the images are now a combination of the features. Okay, so so that was an overview. Now I just want to give you an idea of an MNIST image database. So there are lots of databases that exist. So MNIST is one of those which is based on, it's got a large number of handwritten images. Okay, these are handwritten digits, and that's a database, and it's been applied for neural networks, and you can do that as well. So that was just a quick shot at what an MNIST image looks like. Okay. Now let's try to understand neural networks in a little bit more detail. Okay, you've got a fair idea of the overall idea, but now we need to do some get into a little bit of the arithmetic and try to see how does it actually work, and also try to see what are the parameters involved. So we need to understand how the layers stack up. If you have a deep neural network, how do the layers start to stack up? And how many parameters, because as the network becomes bigger and bigger, the number of parameters becomes bigger and bigger as well, okay? And so it becomes more complex. Just recently, I don't know if you've heard about it, there's something called a GPT-3, which is one of the most recent neural networks which is being applied to speech recognition, all right? Speech recognition and generally, in that area. So, and this has come out from, I think, OpenAI, which is owned by Elon Musk. I don't know if you've heard of it or not, but just look it up. It does some tremendous things. In fact, if you remember that one of the earliest tests for whether an AI machine passes, you must have heard of the Turing test. Okay, how many of you have heard of the Turing test? Okay, some of you. So the Turing test was developed by Alan Turing way back, I think about maybe 50 to 100 years ago. I don't remember exactly, I think in the early 20th century. And Alan Turing basically proposed the idea that if you wanted to find out if an AI machine truly has general intelligence, okay? Remember, all of this that we're doing in machine learning is not general artificial intelligence, it's very narrow AI. Narrow AI basically means that you can use this particular network for detecting images, for example, but you can't use it for example, speech recognition, okay? But if you had a general purpose AI, in other words, if you had a robot and it could do everything that a human being can do, it can think like a human being, that would be called general AI. And people really don't know if general AI will ever be achieved, because there are some people think that the human brain is so unique that a computer, no matter how sophisticated, how many neurons you can build into it, would never be able to actually have self-consciousness. Okay, and self-consciousness basically means that you've seen all of this in movies, in some of the famous movies where the computer or robot eventually becomes self-conscious, and that's the end of humanity, right? That's when the robots take over the world. So the Turing test was basically saying that if you can, if you have behind, let's say, an interface, if you were interacting with a human being versus a computer, and if you could actually write questions and you could engage in a very long dialogue, and if you couldn't figure out the difference between the human being and the AI engine, then that means that the AI engine actually has general intelligence, which means that you could talk about anything under the world, right? You could ask it, how do you feel today, right? And you know, it's philosophical questions. Do you believe in God? And what is the, where do you think that, what is the end of the universe? Very difficult questions. And human beings ultimately can give you answer very philosophical questions. But AI engines, whether it's machine learning, the most sophisticated engines, generally fail at some point. Okay, simply because they are not able to understand human language as well. Okay, so GPT-3, by the way, recently, last year GPT-2 from Elon Musk's company, it had about 1 billion parameters. Okay, now what do parameters mean? Parameters means how many weights exist in the network. Okay, the GPT-3, which is released, I think recently in the last few months, it has about 175 billion parameters. Okay, 175 with 9 zeros after that. And today, if you interact, and this is all available online, so if you go on, and if you actually try to interact with it, you can ask it. You can have a fairly long conversation, and it'll actually be able to understand what you're saying, and be able to give you fairly good responses. Okay, so it's getting close to a general purpose AI. Okay, not nowhere close, but I would say it's a step in that direction. Okay. Another thing very interesting that it can do is, for all of you computer science, this should be an alarming signal of alarm, is that it can actually write code. Okay, you can say that write a code, write an algorithm which is able to produce an interface which is similar to Google, which I can do a search. Okay, write a search, sort of a search engine interface. So it'll be able to write a search engine interface. So you can experiment with this. So just look up GPT-3, and you'll find it does amazing things. Okay, but the reason why I'm talking about all of that is because the number of parameters, because today the networks have become so complex, because hardware resources are now available, you can design very deep neural networks with a very large number of parameters. So as I was saying, it's got 175 billion. I think that's the most sophisticated neural network, deep neural network that exists today. Okay, and it's doing absolutely amazing things. It's writing code. So we need to understand, how do you actually determine the number of parameters in a network? So that's what we're going to try to do in the remaining time that we have left. Okay, so let's first of all try to understand, if you have a convolutional network and if you have a filter, what is the mapping between the convolution and the neural network? Okay, now in a neural network, we know that you have, in a normal neural network, you have inputs and you have outputs, right? So what do you think is the mapping now? Do you think this is an output, or is this an output? How do you convert an input to an output? Okay, how do you convert a two-dimensional image into an input into a neural network? We've seen some examples of this. So let's say it's a W1 by W1 image. How do you think it will be converted into an input image which looks like X1 se lekar ke Xn tak? So you just flatten it, just stretch it. Okay, so you could do it like this, you could do it anyway like this, and so on, but you simply stretch it out. Okay, what would be the value of n? W1 squared. I'm assuming that the height is the same as the width, so I'm just calling it W1 times W1. Okay. What will be the output? Will the filter be the output? Will W2 be the output? Where's the activation map? Is this the activation map? Clearly no. This is the filter. Okay, we are applying this filter, we are convolving with it, and we have an output. The activation map is over here. Okay. We know how W2 depends on W1. We already know that W1 minus F divided by S plus 1, right? So we know W1 is a function of W1. W2 is a function of W1. And it's a function of the filter size as well. Okay. Now, the output is clearly what? This is going to be the output, right? So this would be Y1 se lekar ke Y, let's say M tak. Okay. And M would be what? So the output layer would be W2 squared. Okay. What about the filters? How do the filters come into the neural network? We early talked about it, right? So this could be a fully connected neural network, right? This is not there in the middle. Okay. So this is not there. You simply have a fully connected network which is taking the input and converting it into an output, which is the activation map. Where do you think are the filters coming in? Where's the filter coming in? The filter is actually the weights, right? So the filter maps onto the weights. So for each output, right? How many weights should there be? So there should be n1 squared weights. Is that right? If it's fully connected. Okay. Sorry, n1, not n1 squared. That's w1 squared. Okay. So that's the simple case. Now let's take a slightly more complex case. Okay. So basically for each input over here, what you're going to do is you're going to take the output over here, and the output needs to be calculated based on a particular, you put this filter over here, right? And you try, and how many weights are actually over here. So you're not really convolving it with the entire thing at one time, you're convolving it piece by piece, right? So how many, what would be the number of weights over here? 1 से लेकर के कहाँ तक जाएगा ये? Filter की size total कितने हैं? It's f by f. So it will go up till 4. So it will be f squared, right? So in this particular case, where you actually have a small filter, which is smaller than the original image size, the output, the number of weights per pixel is going to be how many? It's going to be f squared. Okay, and we'll call this parameter. What am I calling this parameter? I'm calling that right. I'm calling that m. Okay, so m is the number of weights per pixel. Okay, at the output activation image. All right, is that clear? Now let's keep on making this a little bit more complex. Okay, now suppose that you have a 3-color image. All right, so this is now, I've shown it slightly differently. Instead of the image being like this, I've shown it in 3 dimensions. So your input weights, the W1 is going to be over here, and W1 is going to be here. So this is now 3-dimensional. Okay, so if I call this the depth D1, what is D1 going to be equal to? 3, because it's red, green, blue. Okay, and most typical images which are in color are represented as follows. Okay, now you've got a filter which is f by f. Now you normally also introduce 3 separate filters for each one of the different RGB colors. Okay, that's how it's normally done. You could have a single filter for all of them, but you generally what you want to do is you want to be able to differentiate between the 3 colors. Okay, because they all may have different meanings. Okay, so you apply a filter which is an f by f by a certain depth. Okay, and the depth will be the same as the input depth. Okay, so this is W1 by W1 by D1. Okay, this is the input image. This is the filter. And so for each one of these, now what will M be equal to? Okay, so for each output pixel over here, how many weights are there going to be? So first of all, will you have a single activation map, or do you want to have the depth over here is D1, right? Let's say D1 is 3. So do you want to have 3 output maps, activation maps, or you want to have 1? You'd want to have 3, right? But I'm telling you how it's normally done. And I'm not saying that this is the only way, right? But the first, let's say, as I mentioned earlier, there's a competition called ImageNet, right? That has been taking place for the last maybe 1.5 decades. Now, in 2012, the earlier non-neural network-based networks were, since 2012, have now been beaten continuously from 2012 onwards by deep neural network-based solutions, all right? And the first network that did it was called AlexNet, okay? AlexNet, and it was done by a group in, I think, University of Toronto, which was based on Mr. Heaton, okay? So Jeff Heaton and his group, and I think, I forget the other person's name, who was his PhD student, has got a difficult name, but those are the guys who proposed AlexNet, and this came out in 2012. And this proposed a certain architecture, okay? And a lot of architectures have come subsequently, but a lot of the key architectures, key components have not changed. So one of the things that they did was to use a single activation map for all 3 of the colors, okay? Again, I'm not saying this is the best way. Maybe you come up with a different technique which uses 3 activation maps for each one of the colors, and maybe it'll be perform better, right? We don't know. But this is quite common that they use a single activation map. And so what they do is they sum it up, okay? So they multiply each one of these one by one. They do an individual convolution for each one of those layers, and then they sum it all up, okay? And then they add a single activation for each one of the points, okay? So how many weights would there now be for each output pixel? You've already seen कि जब आपके पास 2 dimension होते हैं तो आपके पास f squared है, right? So now what is it going to be? F squared times d1, right? So now you simply have another depth. So now you've got the number of weights is per output image, per output pixel is now f squared d1, okay? जी जी say that again. Depth, अगर depth same है, इसकी depth और इसकी depth same है, हाँ, f cube. अच्छा, आपका मतलब है कि अगर इसकी depth is also equal to f. Okay, but the reason why d1 is 3, why is d1 equal to 3? First of all, let's look at this. Are you clear why this depth is different from W1 and W2? And W1 over here and W1. Let's say it's a square image, right? And it's in 3 colors. So depth is always going to be 3. Okay. Now what we're saying is we've chosen 3 filters for each one of the 3 colors. Okay. So now the depth is not going to be equal to f. W1 could be, for example, 1000. All right. The depth D1 is going to be 3. The filter could be, let's say it could be 3 by 3, it could be 5 by 5, it could be 10 by 10. Okay. It is generally but a lot smaller than this entire image. Okay. Sorry. Filter is what? It's always going to be square. So typically, because most filters are always generally symmetric. Okay, because images are also symmetric, so you take filters which are symmetric. So let's assume that all the images are symmetric. Now, is it clear that the number of weights for the particular output is only going to be dependent on F and not on W1? Right? Because if you go back to your basics, what we're doing in terms of convolution. So we had an input, we had a filter, and we looked at the output, right? So each portion of the output actually corresponded to the application of this. So we put the filter over here, and we calculated the particular output, right? So each output only dependent on the filter size. Okay, so the number of weights is not going to be dependent on the input image. Each one of these weights, the number of weights for each pixel is only going to be depend on the filter size, okay, and on the depth, but it's not going to be dependent on the size of W1. The W1 could be extremely large, but the output image could be very small depending on how big, sorry, the number of weights over here could be very small because it depends only on F. Okay, so far so good. Now we're going to make this more complex. And now what we're saying is that, as you saw earlier, that you can have multiple filters. All right, हमने क्या filters use किया था? F1, F2, F3, left diagonal, right diagonal, and an X, right? So each one of them is going to be a separate filter. It's not going to be this filter. This filter is only selecting, let's say, a left diagonal, and maybe in 3 colors. Okay. Now you have K filters. So now earlier we had F1, F2, F3. Now in that case K was 3. Okay. Earlier we saw the example where we had 4 filters, right? From the other example. So now we have K filters. Okay. K could be 3, K could be 4, K could be whatever. All right. Now, how is the output going to be? So each point over here is now only dependent on F squared times D1, right? So this is D1, and this is the size of the filter, okay? So this is the number of weights per output pixel. And now the question is कि जब आप एक अलग filter ले रहे हैं, तो should it have a separate activation map, or should you use the same activation map? So say that again. 2 filters, it doesn't make sense, right? क्योंकि हमने अभी तक देखा है कि each activation map, each filter is resulting in a particular activation map. It was selecting maybe a left diagonal over here, right? And this is supposed to select a right diagonal. So if it's selecting a right diagonal, these filters, this is a left diagonal filter, and the other one is a right diagonal filter, okay? So this is left, this is right. So clearly, even though there's a depth over here, clearly you need to have separate activation maps, okay? So how many activation maps are you going to have? K, okay? What is the size of these activation maps going to be? W2 by W2. This is what we had originally designed, right? And W2 depends on W1 and the filter size, okay? Plus 2P if you're doing padding divided by S plus 1, okay? So this is the golden formula that's used all the time for determining the output size, okay? So now let's try to do some calculations, okay? So now let's try to figure out the total number of parameters, okay? The total number of parameters means the total number of weights, okay? So the number of weights, let's call this P, okay? P is going to be what? How many weights do you have for each one of these output pixels? So let's call this N1, Okay, it's going to be N1 times something. N1 is equal to what? F squared into D1, right? So this is D1, this is D1. Okay. Now, this is the number of weights for this particular point, right? How many of these do we have all in all? So how many do we have in this particular filter? Times W2 squared. W2 squared into ये इसमें W2 squared parameters हो गए, and each one of these can be thought of as a neuron, output neuron. So a pixel can be considered as an output neuron. Okay, so if you look at the number of neurons that exist over here, how many neurons are there? Number of neurons, which we had earlier defined as M is the so all right, I made a mistake over here. This I'm going to call as N1. Okay, so this is N1, right? Number of weights per pixel. Okay, so N1 is equal to F squared D1. And how many neurons do we have all in all in the output? Sorry? W? Which W? W2 squared into K. Okay, very good. So you've got W2 squared into K. This is the value of M. Okay, number of neurons, this is M. Okay, so I've got N1 times M. So basically what we're saying is take the total number of neurons in the output, multiply it by the number of weights per neuron. Okay, and this gives you the number of parameters. In other words, these are all the weights. This is the total number of weights. So this one is N1 and this one is also N1, right? But you have how many of these? You've got W2 squared times K, you have M of these. This is the first one and this is the Mth one. Okay, so you can think of this going from here all the way up to here. All right, so the entire output image, each one of them has got a separate weight. Okay, so we've got a very large number of weights. Okay, now imagine that you have, let's say, an image which is 1,000 by 1,000. Okay, so this is 10 to the power 3 times 10 to the power 3 times 3 times W2 squared. So let's say you have a filter of size, let's say a filter is much less than the size of the input. Okay, suppose the input is W1 is 1,000 and the filter, let's say, is only size 3. Okay, in that case, you can say that W2 is basically approximately equal to W1 minus F times some padding divided by S. Let's say assume K, S is equal to 1. Okay, plus 1. So you can see that this is negligible, this is there. So this is approximately W2 is approximately equal to W1 if S is equal to 1, if the stride is 1. And normally in neural networks, unless you're doing max pooling, you keep the stride 1. Okay, so you can see how big this is going to get. How big is this going to be? W2 is equal to W1. So this is approximately, again, W3 times W3. And now it also depends on how many filters you want to select. So how many filters should you have? Is that something that can be decided by the architect of the neural network? Or is that something that's dependent on the input, the size of the input? Sorry? It depends on the input size. So let's say if the input is 1,000 by 1,000, right? It's a typical image. let's say 1000 by 1000, would the number of filters, would the size of the filter, would the number of filters, K, okay? You have K filters over here, 1 se leke K tak. What are the variable parameters? What do you have in control? And what parameters are dependent on the input? And what are, as you are the architect of the neural network, what depends on you? The number of filters depends on us, right? So for example, you selecting an O. How many filters did we thought it would be appropriate? 1, 2, 3, 4. Sorry, 1, 2, then 3, and then the horizontal 4. So ideally, we need to have 4 filters to determine an O. How many filters do you think we need to for an X? 3 is good enough, right? So so if we're looking for an X or an O, how many filters would you want to have? You want to have 4, right? 3 से क्योंकि O detect नहीं हो रहा है, तो we need to have 4. 4 से O हो जाएगा, which is a little bit more complex. Now imagine if you're trying to detect a human face. How many filters would you want to have in the first layer? I mean, you can imagine how many different types of edges you want, right? We saw that in the earlier example, we had 4 filters which were detecting, 2 vertical and 2 horizontal, right? So actually the number of filters can be very large. It depends on how complex an image that you want to detect. And you'll see in examples that the number of K could be as large as 100, okay? Can be 200, can be, can be smaller as well. But does the number of parameters depend on K? It does, right? So if you make K very big, then it is directly proportional to K. It's not proportional to K squared, but it is proportional to K. So you may want, it's linearly proportional, which means that yes, you could go with 10, you could double it, 20. It's not going to, if you go from 10 and you go to 20 filters, if it's the 10 filters, if 10 filters is taking, let's say 1 hour, how long do you think 20 filters is going to take? 2 hours, right? Because it's linearly proportional, right? But now suppose you take an image which is of size 1000 and it's taking 1 hour, and you take an image which is of size 2000, how much longer do you think it's going to take? Sorry? Twice the time. Look at the math. Look at the math over here. Huh? So the question is, आपने एक image लिया, it was size 1000 by 1000, right? Now you want to have another image which is size 2000 by 2000, okay? The 1000 by 1000 image took 1 hour, all right? So I'll write it over here. 1000 by 1000 took 1 hour. The 2000 by 2000 will take how long? It'll take 4 hours. Why? Because you think that the output, the computing output is proportional to the square, okay? But think again, look at the output, look at the number of parameters. Do you think the computation is proportional to the number of parameters? We don't really know, but perhaps it is. If you're doubling the number of the number of weights in the entire network, you might think, if you think back, what are we doing in the gradient descent? अगर आपके पास W1, W2 है, and now you have you've got twice the number of weights, you think the gradient descent algorithm will become twice as complex? Yes. So I think it's proportional to the number of weights, okay? Now the number of weights are called what over here? Number of parameters, right? So the computation is now proportional to P, right? Now, if you double the size, how does P change? So we're changing the size of W1. Okay. So how does the output change? यहाँ पर मैंने एक मिस्टेक की बाय द वे, यहाँ पर मैंने 10 पावर 3 क्यों लिखा है? Nobody corrected me. ये क्या होना चाहिए? This should be size f. So f squared कितना है? f कितना हमने यहाँ पर चुना है? Let's say कि f is let's say 10 by 10. Okay. So this should be 10 by 10 by 3. So this is not dependent on the input, but this parameter is dependent on the input, right? So if we double the input, so this is going to, instead of becoming 2, is going to look like this, and this is what it's going to be look like. So it's going to be 4 times the original size. So whoever said it's going to be, if you double the input size, W1, the output, if it's going to take 1 hour, the output is going to take 4 hours. Okay, so far so good. Okay, if you double the size of k, then the output is going to double only. It's not going to quadruple, it's going to double, right? If you double the size of the filter, what's going to happen? It will become squared, right? Because it depends on this, on the, it's dependent on f squared, okay? हाँ, so अगर आप बिल्कुल सही है, अगर आप filter size बढ़ाएंगे तो ये W2 थोड़ा सा कम होगा, लेकिन if you assume कि the filter is much smaller, then शायद impact नहीं हो, but you're right, थोड़ा सा impact कम हो जाएगा, ठीक है? So you've got an idea of the complexity of this particular computation, okay? अच्छा, now there's something called parameter sharing, okay? Parameter sharing basically says कि ये जो particular pixel है, इसके जो weights हैं, do you think कि इसके जो weights हैं, और let's say I'm going to delete this. I'm going to delete this, okay, for a minute. And let's say कि I'm drawing a line over here. Okay, so these are the weights. These are weights for a particular pixel over here, particular neuron over here. Let's call those are N1, right? N1 weights over here. These are also N1 weights over here, okay? And you could have, similarly, you could have weights over here, you could have weights over here, you can have lots of weights. Now, parameter sharing basically says that the weights, if you find the weights over here, you've done a lot of training, right? And if you find the weights associated with a pixel anywhere on the particular image, then the weights should not be different over here. Okay, let me repeat. The weights for a pixel over here, if you do the training, should not be different from the weights over here. Okay, so in other words, let's say okay, you have a 2 by 2 output, okay, and आपकी filter जो है, let's say that's also something like this, that's also 2 by 2, and you're calculating this. Okay, it's got 4 weights, 1, 2, 3, and 4. Okay, similarly, इसके भी 4 weights होंगे, 1, 2, 3, 4. Okay, now parameter sharing basically says that if you train this network, then these 4 weights and these 4 weights don't have to be different. Okay, now can you sort of try to justify this? Why do you think that is the case? Why do you think that parameter sharing can be applied? Okay, and if, for example, we do apply parameter sharing, the number of parameters कितने कम हो जाएंगे? I'm only saying within a certain image. Within an image, all the weights are going to be the same regardless of the neuron. So W2 squared times कम हो जाएंगे, right? But this image, this is going to have separate weights, but all the weights over here are going to be the same. So in other words, you're going to reduce the number of parameters by W2 times W2. Okay? So you get these two cancel out. So the number of parameters with parameter sharing comes out to be N1 times M. N1 was earlier F squared times D1. And now M comes out to be the number of neurons are only going to be K. Okay? Because all of these are going to have the same weight. So in other words, अगर let's say कि ये जो neuron है, इसका जो weight है, suppose this is 1, 0, 0 and 1. Okay? तो इसके जो चार न्यूरॉन, ये जब ये कनेक्ट करेगा इस फिल्टर के साथ, तो इसके भी जो चारों वेट्स होंगे वो 1, 0, 0 and 1 होंगे. In other words, this set of weights is going to be the same as this set of weights. So the question is, why do you think parameter sharing makes sense? I mean, people have actually applied it on real networks. What they've done is they've said that parameters hum kam karna cha rahe hain, right? Because parameter sharing, as you can see, W2 is dependent directly on W1. So if you can reduce and if you can have parameter sharing, what does that mean? Does the complexity now then depend on the size of the input? It doesn't depend on the size. So parameter sharing basically says that if we can do parameter sharing, then the number of parameters does not depend on the size of the input. The input could be 1,000 by 1,000 or it could be 10,000 by 10,000. The computation complexity will only depend on the filter size squared, the depth of the filter, and the number of filters. Okay, it will become completely independent of the size of the input, because we're saying that जो weights हैं, हर input point के, all the weights can be the same. Okay, and the logic, let me explain to you the logic. The logic basically says कि अगर आपके पास एक image है, right? Let's say I'm detecting a diagonal over here. All right, I'm detecting a diagonal over here. So the diagonal could be anywhere in the image. Okay. And as long as we're detecting the diagonal, it doesn't really matter where it's in the image. Okay. So if we're detecting an ear over here and we're detecting an ear over here, it still says that there is an ear in the image. There's a face in the image. We don't really mind where it is. Okay. So the fact that you don't mind where it is in the image implies that the weights over here can be the same over here. It's a little complex point, but this is the rough justification. Okay. Okay, so what you're talking about is the topic of our next lecture, which is something called regularization. Regularization basically says that you want to stop overfitting, okay, and you want to have a result which is somewhat, अगर आपके पास 1000 images पर आपने train किया है, तो वो overfit ना हो जाए कि जब तक कि वही बिल्ली जब तक कि नहीं होगी तो वो fit करेगा, वो बिल्ली अगर हल्का से curved भी चली गई तो फिर नहीं करेगा. So that's called regularization. You want to have generalized results, okay, and we're going to discuss that in the next lecture. How do we achieve that? Okay, जी. हाँ. Sorry? W2 का हमने कैसे कम कर दिया यहाँ पर? नहीं, f squared times d1 तो है, n1 की जो है, right? So the number of weights remains the same, number of weights per neuron. Like, and what we're saying is that the total number of neurons, instead of treating each one of these as separate neurons, we're going to treat all of this as just one big neuron. Okay? And how many neurons are going to be there? There are going to be k neurons. Because what we're saying is that for all of these neurons, we just need to have one set of weights. Okay? And why is that? Because of the property that the image, and this is sort of a hand waving kind of an, it's sort of an intuitive argument. Okay? What it's basically saying is that it doesn't depend where an image is. Okay? The image could be anywhere. And the weights, what you're trying to detect over here is equally applicable over here. Okay, so the weights, if you want to make the weights for this particular pixel the same as this particular pixel, it doesn't really matter. They can be made the same. Okay. So this is again a slightly fine point. Okay, maybe I'm not able to completely explain this, but and you're right, there's complexity as well. But as you go further, think about it as well, and look at some of the. If you're trying to get a better grasp of it, this will require a more detailed explanation, and I'll see if there are better explanations of it. But very roughly speaking, it says that an image, it doesn't really depend on where in the image are you detecting a particular object. Okay, very vaguely explaining that. Okay, so that's the basic concept behind parameter sharing, and that results in a reduction in the number of parameters by W2 squared, and so the output, the number of parameters only becomes P now becomes equal to F squared D1 times K, which is a huge reduction. So you can imagine that if this is 10 by 10 filter, 10 squared, D1 is times 3, K1 is, let's say, 20 filters. All of a sudden, that 1,000 by 1,000, that 1 million has become extremely small. It's been reduced by 1 million. Okay. So that's parameter sharing. So it's 9 o'clock now. So let's stop over here. And in the next time, we'll take a look at some more examples and see how this is also applied. G. Say that again. It is reducing the size of the memory because the number of parameters is reduced. Okay, so remember, every time you're doing back propagation, you're going to be updating every weight. Okay, so if the weights, the number of weights or the number of parameters, as you call them now, are reduced by a factor of 1 million, then you have to, that's 1 million less parameters that you have to update using gradient descent. Yes, we will update it for every neuron, but the number of weights that have to be updated is 1 million times smaller. Okay, because if you've updated these weights, we know that these weights are going to be the same. So these weights are not independent. They're all dependent on the same. Okay, they're all the same weights. ठीक है ना?